Okay, so it's 2 o'clock, so I think we can make a start. Thank you everyone for coming. I just want to point out at the start here that this webinar is being recorded and will be made available online later. So hello and welcome everyone to today's Ocean Ice Work Package 5 webinar on ice sheet impacts on global ocean circulation. My name's Kylie Owen and I'm moderating the session today. I'm a marine mammal expert and an officer for the European Polar Board and the European Polar Coordination Office. Ocean Ice is a Horizon Europe project that is funded by the European Commission and UKRI. Ocean Ice assesses the impact of key Antarctic ice sheet and Southern Ocean processes on planet Earth via their influence on sea level rise, deep water formation, and ocean circulation and climate. Within Ocean Ice, the European Polar Board leads the webinar series, presenting the objectives and ongoing developments across the project's work packages. Today, our webinar focuses on Work Package 5 that examines the impact of ice sheet meltwater discharge on deep water formation and export from the poles, and the ultimate impact upon large-scale ocean circulation, including the AMOC and the ACC. We are delighted to have an excellent lineup of speakers today. We have Petra Langebroek introducing the program, Rachael Sanders and Zhetao Tan presenting exciting new observational results, Xabier, Davila, Birte, Gülk, and David Chandler, who will share their insights on water mass, archaeology, modelling results, and the global impacts of freshwater forcing. Please post your questions in the chat during the talks, and after each of the sessions, we'll try to take 1 or 2 short questions, and then we'll have a more detailed Q&A at the end of the session, all the sessions. And so with that, we can get started. I would like to introduce Petra, who will introduce Work Package 5. Petra is a research director at NORCE and the Bjerknes Centre for Climate Research in Bergen. She has a strong background in ice sheet and climate modelling. She studies how the Antarctic and Greenland ice sheets have changed in the past, how they may evolve in the future, and what this means for global climate systems. So Petra, the floor is yours.
Hello, everyone. I hope you can see everything right here now. So my name is Petra Langebroek indeed. Thank you for the nice introduction, Kylie. And together with Elaine McDonagh, I'm leading the Work Package 5 in Ocean Ice. And our work package is conveniently, like the title of this webinar, called Ice Sheet Impacts on Global Ocean Circulation. But I have to give you a little heads up because we are all working with the Antarctic ice sheet. So actually what we are talking about mostly is the Antarctic ice sheet impacts on the global ocean circulation and not so much the part from the Greenland ice sheet. So Ocean Ice is a European project. So all of us researchers, or most of us, we are based in Europe. And even though we work with Antarctica, we also realize that Antarctica, for most people in Europe, is just seen as something at the end of the world, at the end of the map here in the south, something very far away and maybe not even so relevant. But this is really a matter of perspective, because if you would use this map, for example, which is created by one of our colleagues in Ocean Ice, then you can see Antarctica in the center of the world. And actually, Antarctica is the place where all the large ocean basins connect together. So we have the Atlantic Ocean, the Indian Ocean, and the Pacific Ocean all meeting up in the Southern Ocean, the ocean around Antarctica. And if you see this picture, it's maybe easier to imagine that if there are any changes in Antarctica, for example, additional ice melt or calving or so, that this would influence the different global oceans. In the Ocean Ice project, we also have an interesting map view. Here we put Antarctica on the top of the map and then flip down the rest of the world upside down on the bottom. So again, to emphasize how important the Antarctic ice sheet is in this project. And in the top row, you can see the various processes that are studied in the Ocean Ice project. For example, we focus on how warm water intrusions can influence ice shelf melt from below. And also we focus on ice shelf dynamics. So for example, calving or changes in the ice shelves themselves. In the central middle part, you see the Antarctic ice sheet. And this is to indicate also that we have a lot of focus on atmospheric processes, how they change the ice sheet in the Ocean Ice project. And then where you see the number 4, this is indicating the work we do with establishing future ice sheet fluxes or finding out what we could expect from future ice sheet changes. And all of these top rows, if you're interested to know more about it, you can look at the website. And actually, there are different webinars explaining the latest research on these topics. So feel free to look at the EPB website's YouTube channel as well for this. Today, we're focusing on what's here indicated with number 5. So what is the impact from Antarctica on the ocean? And we can look at this in different ways. Of course, in order to understand what the impact is on the ocean, we also need to know more about the ocean itself. So luckily, there are lots of observations everywhere in the global oceans. But actually around Antarctica and in the southern oceans, we do miss still key observations. So part of our work is focusing on getting observations from these key locations that are very important for the our understanding of the global oceans. And of course, also there are lots of observations that are already there. And we use new techniques to try to get the most out of these observations so we can make new connections and understand new processes by digging into these already existing data sets as well. And then in order to think about the longer time perspectives and process impacts, we use ocean and Earth system modeling. And today, you're very lucky because we have 5 earliest career researchers that will all tell you about these different parts. So this seminar will bring you to look into data from the South Sandwich Trench and South Atlantic by Rachael and Zhetao. Xabier will talk about water mass archaeology, and Birte and Dave will talk about ocean and climate modeling. So with that, I again also wish you all welcome to this webinar, and I hope you enjoy all the nice talks that we have aligned for you. And with that, I'll give the word back to you, Kylie.
Yeah, excellent. Thank you, Petra and Elaine, for the nice introduction to Work Package 5. So yeah, now we'll move on to the second part of the webinar that's related to observations with Rachael and Zhetao, presenting us new observations by the Ocean Ice Project. Rachael Sanders is a physical oceanographer at the British Antarctic Survey. Her research ranges from investigating the impact of sea ice variability on Southern Ocean water masses to understanding the controls of deoxygenation in the North Atlantic, bringing a broad perspective on ocean climate connections. Rachael will present to us the first time series of deep observations from the South Sandwich Trench. So thank you, Rachael. I'll hand over to you.
Thanks, Kylie. Okay, you see that okay? Cool. Okay, so yeah, I'm going to be talking about the observations that we got from 2 moorings that we deployed in the South Sandwich Trench between 2024 and 2025. So why do we care about the South Sandwich Trench? Well, it's the deepest region of the Southern Ocean, and it's a major export route of Antarctic bottom water from Antarctica out of the Weddell Sea into the ocean basins. So Antarctic bottom water is the coldest and densest water mass. It forms in the Antarctic shelf seas before being exported at the seafloor to all the ocean basins, and it's the largest water mass volumetrically. So over 50% of the Antarctic bottom water that is exported out into the rest of the ocean basins goes through the Weddell Sea. And that's what we can see here. So within the Weddell Sea, we have 2 different water masses comprise that bottom water, and they are the Weddell Sea bottom water, which is in orange here, so mainly stays circulating within the Weddell Sea, and the Weddell Sea deep water, which is the dark blue arrows. And this water circulates around the Weddell Sea, and then some of it escapes via specific export routes. So some of them we can see here along the South Scotia Ridge, including at Orkney Passage, where we can see this star. And that is a region that we've been monitoring for many years. But there is also this other export route that goes through the South Sandwich Trench. And that's somewhere where we've never had a long time series of observations before. And that's why we were deploying this mooring in this region. And in recent years, there's been a freshening and a warming of this water mass. So it's important to understand how this is affecting the export route and how much and the properties of the water that is transferred to the other oceans. So Earlier this year, we recovered 2 moorings from within this red circle. So these are the South Sandwich Trench moorings, the central and the western mooring. They're marked here. At the same time, we recovered the other moorings. So as I mentioned from the Orkney Passage, where we've had moorings for many years, and we recovered 2 of the moorings there. And also this M3 mooring, which is in the north of the Weddell Sea. So that's closer to the source of the water. So we're expecting the bottom water to be exported past this M3, and then some of it will go through Orkney Passage and escape that way, and some more will be exported through the South Sandwich Trench instead. So just a description of what a mooring is. It's basically a very long rope. So the central mooring that we deployed was 4,500 meters long, reaching depths of around 6,000 meters. And it's got a weight on the bottom to anchor it to the ground, and then floats to keep it buoyant, and instruments at different depths along this rope. So on the central mooring, we had 4 current meters giving us velocity measurements, 2 CTDs that tell us the temperature, the salinity and pressure, and then 3 temperature sensors. And these were recording around once every 5 minutes, depending on the battery life and the memory of the instruments. Okay, so this is a cross-section of the South Sandwich Trench where those moorings were deployed. So this is the central mooring. You can see it's on sort of the deepest point of that cross-section in the middle of the trench. And then the western mooring is shallower, so it only reaches around 4,000 meters. And that's on the slope, the western slope of the trench. And the moorings were designed for the instruments to capture the variability within the different water masses at different depths, and to capture the main export route going through that trench. And so in February this year, we successfully recovered the central mooring, but unfortunately, when we went to recover the western mooring, the wire above the second instruments had broken and potentially snagged on an iceberg. But it meant that we only recovered 2 of the instruments on that mooring. And because there wasn't enough floats on the mooring left to keep them up, those were most likely lying on the seabed for the whole deployment. So we don't have as much data from that mooring, but we do still have some data that is useful. And we have lots of data from the central mooring. So this is the temperature time series that we obtained from the central mooring. So we have temperature time series from between 1,500 meters, shown in blue, right down to the Antarctic bottom water at the seafloor, and that's around 6,000 meters in green. And you can see there's plenty of variability within these time series. Obviously, because we only have a year of data, it's difficult to tell what is a seasonal cycle and what is intraannual variability. But we're hoping to be able to work that out more by comparing it to the other moorings that we have longer time series from as well. And there is plenty of variability to understand in here, and different variability at different depths. We also have lots of current speed data. So this is the absolute current speed from different depths that we had current meters on the mooring. And we've got some significant variability that is present at all different depths here, which suggests that there's a barotropic response happening, probably due to the winds. We need to look into that more. But we are seeing a lot of variability that is the same in the different water masses. And on the right is the average current direction for each of the depths. So if you can think back to that map of the South Sandwich Trench at the beginning, so that is this is mostly going northeast, which is along that trench, so along the export pathway, which is exactly what we would imagine. And then we do still have data from the western mooring. So this is current speed data and temperature data from the 2 instruments that we did recover. And we assume that these were either at the seafloor or somewhere trapped, like caught on the rope near to the seafloor. So we have to assume that these were around 4,000 meters. And because of the way the current meter works, we can only trust the absolute current speed of this one, not the individual velocities. So we don't know much about the direction, but we obviously have the central mooring that was very close to it, so we can use that to further understand it. And the data that we've got back from this mooring also looks quite similar to that from the central mooring. So it gives us a lot more trust in the data and that it is usable. So we haven't done a huge amount of interpretation of this data yet. Mainly, we've just been processing it and doing the quality control up to now. But the first thing we're going to start looking at is comparing it with the other mooring instrument, the other data from the moorings that we also recovered. So if there is a signal that's going to be transported in this bottom water, we expect to see it first in the M3 mooring, which is closest to the source of that bottom water, closest to the Weddell Sea, and then through up to Orkney Passage, and then along the pathway to the South Sandwich Trench if it reaches there. So we've started comparing the data from the deepest instruments at each mooring. So even though these are at very different depths, they're still within the Antarctic bottom water at each of these moorings. So we have the two South Sandwich Trench, central and west, and then the OP3 and OP5 is the Orkney Passage moorings, and then this M3 mooring, which is in the Northern Weddell Sea. And there's obviously very different variability in these moorings. We can see that the yellow and purple lines are quite similar because they're both the Orkney Passage data. But if we just do quick lagged correlations between the South Sandwich Trench central mooring, so that's the main mooring that we got back. If we look at the current speed anomaly at the deepest instrument and compare that with the deepest instrument of the other moorings, we can see that there's quite a strong correlation around zero lag between with a very short lag next to this with the South Sandwich Trench west, and that's what we expect just due to the proximity of the moorings between each other. But we also get these spikes, and obviously we've not looked at the significance of these or anything yet, but we do see something that looks similar in OP3 and OP5, and that's at 0 days. So again, it is probably a barotropic response due to the winds. But at the same time, we see the complete opposite at M3, and this is something that we need to look at. This is just the first thing we're going to look at to work out what's causing this. And we don't see the similar kind of relationship in temperature, because if the temperature anomalies are being transported across this export pathway, it's going to take much longer for that to happen. So the next steps are we're going to be doing a lot of comparison with the other mooring data, and we need to work out exactly what timescales we would expect for any signal in the Weddell Sea to reach the South Sandwich Trench to see if we are going to see this within the 1 year time series. And we need to look at the role of winds, if it's the winds driving this barotropic change. Previous work has shown a lot of evidence that the wind drives variability in the export of the Antarctic bottom water at Orkney Passage. So we want to see if that's the same in the South Sandwich Trench. And then whether what we're seeing is seasonal variation or interannual, just based on what we're seeing in the other moorings as well, where we've got much longer time series. And later in March next year, we'll be recovering the M2 mooring, which is another one in the Northern Weddell Sea. So that'll be adding another data point. And then there's other moorings in the area that we're hoping to use this data to also try and understand what is going on with these pathways and how long it's taking any variability in the Weddell Sea to reach these different moorings if we see it still in the South Sandwich Trench. So thank you very much.
Thank you, Rachel. I would now like to invite Zhetao Tan. Zhetao Tan is a postdoc fellow at Laboratoire de Météorologie Dynamique, École Normale Supérieure, working on the Ocean Ice Project Work Package 5. His research interests include physical oceanography and operational oceanography, with a particular focus on ocean observations and data quality improvements, water mass, ocean compound climate change from global to regional scale. He is also now a member of the International Quality Control Ocean Database and the SUP-XBT data management team. Zhetao will present to us new observations on water mass property changes in the South Atlantic. So over to you, Zhetao.
Okay, thank you so much. So here I would like to give you some presentation about the new observation on water mass property change in the South Atlantic. So I would like to first give you a quick overlook of the global view of the ocean observation. And it is about 100 years ago, and since the Nansen introduced the Nansen bottle, so it marks the beginning of the modern area of the global ocean observations. And over the past 100 years, and we collect millions of profiles from temperature, salinity, oxygen, pH, and so on. And this was deployed and collected by XPT, CTT, Argo, and so on. So because of this observation, so now we can have a more clear pictures of the overview of the global ocean climate state, and we can note how the ocean is changing in a warming climate by this most direct ocean observations. And in the South Atlantic, it is also in the middle of this, and because the South Atlantic is central to the global heat and freshwater redistribution and link it to the AMOC variations. So you can see, so I would like to give you a quick overlook about the ocean observations network in the South Atlantic. So you can see in this map, and you can see that there are some key chances that we can put some CDD or some XBT here. For example, the TISA, the gold ship line, the Samba area line, and some XBT line, for example, the AX97 and AX18 lines. And some of these chances are still active at present. And besides of the transits, we also have some Argo flow, and since 2005, for example, these are deployed by the AOLML, correlates, BODC, CSIRO, and so on. And in addition, in the polar regions and the subpolar fund, and there are some animal-borne profiling, and these are put the sensor to the to some mammals, for example, the sea islands, and then we can detect the polar regions, the physical state, and some other and some biogeochemical state. And I would like to say that the new observation can be included by the new deployment. So with the support of the OceanSide project, and we have deployed an additional 4 microcap to the Samba area line in the 44.5 degrees south. And then you can see in these pictures, and the microcap was installed with the PIES, and these are deployed at the bottom of the water. So this is about in the 400-meter step. So because of these installations, and we can detect the temperature, salinity, pressures, and the salt space, and this can be used to investigate the bottled waters, the transport, and the property change. So there are four additional microcap in this map, and you can see that on the right side, it is mainly working with the South Africa partner, and this was deployed in 2023, two years ago, and the data will be recovered in 1 month. And on the left side, it is the microcap that deployed and deployed with the Brussels people and the Argentina partner, and this was deployed in this year June, and the data will be recovered in the next year. So with this OceanSide projects, and we will have the opportunity to recover the data at the bottom water in the South Atlantic, and the data analysis will be start in next year. And in addition, I would like to highlight that the new observation can be regarded as the old data with the new lights. So in other words, making the old observation usable again. For example, for the XBT temperature data in the AX97 line, we have collected thousands of temperature profile at these transits. But some of you may know that the XBT bias the XBT data has some systematic bias. So with the new bias correction method and the new graded product, and we can now have the current boundary product to so-called gold XBT, and this can help us to detect the Brussels current, the transport, and the physical state of this current, and how it's changing in the overpass 30 years. And in addition, for the oxygen product and for the oxygen observation, and in the Argo flow, there may be some bias in the Argo flow for the oxygen data. So with the new quality control and the new bias adjustment techniques developed by the Grosstedt et al. In 2024, and now this data, it is also useful in the South Atlantic, and we can also detect and to see how the oxygenation are changing in the South Atlantic. So I would like to give you some example with these new observations. So first is about the property change of the cold Antarctic in the medium water in South Atlantic. So with this new observational data, and we can now find that in the cold AAIW, the water is becoming warming, lightening, and thinner. And the thermal effects dominate the density decrease because the salinity are not changed too much. And you can see that in these features, the warming signal, it is really increasing. So we try to use a time of mergence methods and find that for this warming signal, there is a key fingerprint of the anthropogenic change in the intermediate water, and this has been affecting 80% of the basins. And if you see the temperature and the latitude, and you can see that the warming signal, it is propagating from the south to the north in the South Atlantic. And the another example is about the oxygen observations in the Antarctic in the medium water. So the AOU, the apparent oxygen utilization, and this is an indicator of the water age, and higher AOU means the water it is older. So with this new observation, and we found that the AOU in the South Atlantic are showing an interesting patterns. The older water is becoming younger, and the younger water is becoming older since 1990s. So this is a multi-decadal change of the AOU. And in addition, and the correlation between the salinity minimum and AOU in this layer, it is a linear relationship, and this can be indicated how much the impact from the Indian Oceans to the Atlantic. And with the ghost ships data and some new observations, and now we find that the AAIW in South Atlantic seems to have an increased influence from the Indian Oceans over the past 40 years. So these are some take-home messages. So the first I want to highlight is that the new observation can be include the new deployment plus with some old observation usable again with the advanced techniques. And we also deploy some microcap in the sandbar areas, and the data will be collected in 2026. But we still have some open questions, and these can be discussed later. For example, even until percent, we still don't know how many observations are enough in the South Atlantic to deliver the required heat and freshwater change. So this is about the issues about the funding, the balance between the funding and the scientific requirement. And the second one is that we still less many attention in the South Atlantic than the North Atlantic for the observational network. So what shall we do next? So this is also an open question, and I would like to open this for everyone who is interested. So these are my presentation. Thank you so much.
Thank you very much, Zhetao, for that. And so to Rachael and Zhetao for both the nice overview of your work and the observations collected under the Ocean Ice Project. We now have time to address one or two questions, and I do see there's one in the chat which I think was addressed to Rachael, saying, any guess on why the coldest temperature is observed at approximately 3,000 meters and not at the bottom on the central mooring?
Not yet. No, I've not actually done any analysis of the temperature data yet. So it's one of the things we'll be looking into in the variability over depth as well as between the different moorings.
Okay, great, thanks. And yeah, just a reminder to add your questions to the chat, and if we don't get to them between the presentations, we'll have a longer Q&A session at the end. And so we are now moving on to the third section of the webinar that's related to data analysis and modelling results with Xabier, Birte and David. Xabier Davila is a researcher at NORCE whose expertise combines modelling, isotopes and machine learning. He works on ocean ventilation, water mass analysis through inverse methods. He's currently focused on reconstructing past ocean surface properties from present-day ocean interior observations to what he calls water mass archaeology. Today, Xabier will talk about water mass archaeology, tracing water masses to the surface. So thank you, Xabier. I'll hand over to you.
Yeah, thank you, Kelly, for the nice introduction. Hopefully you can see the screen. And yes, what is water mass archaeology? So Petra said, and Rachael also showed, that we don't have so many observations in Antarctica, in the Southern Ocean. So what if we could use global observations to say something about Antarctica, and particularly the Antarctic bottom water? So we developed this method where we can trace water mass properties in the global ocean back to the surface, and in particular the Southern Ocean. So let me just review a little bit what Antarctic bottom water is. So it's one of the main water masses that we have in the global ocean, and it's formed through sea ice, ocean and ice shelf interactions, and particularly sea ice formation is very important. And this is why it's quite difficult and challenging to observe this water mass at the site of formation, because it's very harsh conditions, especially in winter. So we don't have so many observations, but those observations that we have, they have indicators that Antarctic bottom water has suffer of changes such as thickness. We know that it's been thinning, but also freshening as well.
Sorry, Xabier, we actually see the presenter view of your presentation.
Oh, yeah, sorry. Does that work?
Yeah,
better?
that's better. Yeah, thank you.
Yeah. So yeah, Antarctic bottom water has been changing, and one of the things that we see in this is a paper that we just published a few days ago, is that both the salinity but also oxygen isotopes, stable oxygen isotopes, have changed, and these changes in both salinity and these stable oxygen isotopes indicate that Antarctic bottom water has freshened due to a decline in sea ice formation. And this is also aligned with some other papers that also show these changes in time. And this particular from Alessandro Silvano shows that salinity has decreased from the 70s up to 2010, and then this trend has reversed and then increased in salinity. But you can see that we don't have so many observations. So we have enough observations to calculate trends, both for salinity and also oxygen isotopes, and say something about the kind of general direction of the changes, but we don't know how much this is part of a change in the state or is part of a longer variability. And this is particular for this 2010 to 2020 reverse of the trend. So we open here the idea of using this water mass archaeology approach to reconstruct this variability of Antarctic bottom water. And for this, I want to introduce this term, Green's functions. So imagine you can follow the water from A at the formation site to B in the interior, an interior point. And you follow this as a function of time. So then you have this kind of bell-shaped distribution where you have no water coming to B from A, and then you will have the bulk of water, and then maybe like a long tail and no water anymore. And these Green's functions connect the surface to the interior, and we can use these to say something about past variability at the surface. And once again, to remark how Antarctic bottom water spreads in the global ocean. So these are the fractions of Antarctic bottom water in the global ocean at the points where we have salinity and stable oxygen isotopes. And we want to look at these two key variables because they tell us something about sea ice. And this is the variables we want to reconstruct. And you can see that some of these fractions are very high, especially in the North Pacific. And these are also very long time scales. So here we are sampling water that is maybe 1,000 years old on average. So there's lots of information there that we can extract. So how do we do this? So you can imagine intuitively that if you know a surface property at A, at the surface, and you know how A connects B through these water mass pathways or these mixing pathways, then you can reconstruct the interior property evolution. And this is what we did a few years ago for anthropogenic carbon, but you can imagine that you can do the opposite. So if you start with your interior properties, these observations, and you combine this with the mixing pathways, the Green's functions from a model, let's say, then you can reconstruct the surface property. So it's the inverse of the same problem. And this is what we intend to do here. So we want to estimate this surface property that it's shown as a Q here through the Green's functions from inverse circulation model. So this is the total matrix intercomparison model, or TMI, and this was developed more than 10 years ago by Xabier and Peter Hivers. And the idea here is that they use tracers, temperature, salinity, nutrients, climatological fields to infer water mass changes or ocean circulation. And this resulted in a transport matrix of a steady-state circulation. And the key idea is that this TMI is very efficient to calculate, to estimate this Green's function. So it's very, very efficient. And we can then connect the surface to all the interior observations in terms of these Green's functions. And this Y is the locations and the observations where we have interior observations of delta 18O, oxygen isotopes, and salinity. And mathematically, this you can see it here below. This is equivalent to reduce or minimize this cost function, which is represented as a weighted least square problem, where we try to minimize the difference between our observations, so in salinity and delta 18O, and the reconstructed observations. And for this, we find this optimal boundary condition that minimizes all that error. So there is a bit of a method that goes around here, and for the interest of time, I will not go into details, but we find surface property time history that is the optimal for our observations. And this is what I'm showing here. On the left is the trends for salinity anomalies. And there's lots of patterns for some sections and some periods. There is an anti-correlation between Weddell Sea and the Ross Sea, sometimes are correlated, and there's lots of spots that we are still trying to analyze. We didn't have so much time to do this yet. And on the right side, we have this time series of these reconstructions. This is for Antarctic bottom water form in the Weddell Sea, and Antarctic bottom water form in the Ross Sea. And as a first glance, you can see that there is quite a bit of variability, decadal variability, and this kind of nice, I don't know, flowy time series. So we are still trying to see if this makes any sense and trying to compare this with extra observations, because we do have more observations for salinity, not so much for delta 18O. But that's where we are now. This is the same reconstructions, but for delta 18O in space and time. So on the left, again, trends, and on the right, the time series. And we see, again, this decadal variability, which could be related to CI. So we are trying to analyze this as a future work. Just a quick summary. So with this water mass archaeology, we are providing an observationally and physically constrained link between the surface forcing and the interior properties in the global ocean. And we see that there is some interdecadal variability, and this is of a similar magnitude as the changes that we have on the observational record. We are still trying to validate this, but it seems that there has been changes in Antarctic bottom water before the observational record that are of the same magnitude. And we would like to provide some link, some mechanistic link with potentially CIs, following other studies from like Senji Su or Alessandro Silvano, and see if we can provide this kind of link between the interior, but also the CIs forcing. And that's all for me. Thank you.
Excellent. Thank you, Xabier. I would now like to invite Birte. Birte Gülk is a postdoc at LOCEAN in Paris, specializing in physical oceanography with a focus on ocean modeling. She uses ocean models to uncover how freshwater from ice melts spreads through the ocean, altering ocean circulation and ventilation. Birte's presentation is related to the response of the Southern Ocean to recent and projected Antarctic meltwater changes. So I'll hand over to you, Birte. Are you there, Birte? You might be muted. Yeah.
Sorry.
Okay. Yep.
Thank you, Kylie, for the nice introduction. And as you said, I will talk about the response of the global overturning circulation to recent and projected Antarctic meltwater changes. And to start with, like we all know, if meltwater is released around Antarctica, it affects the ocean circulation. And several studies have shown, for example, that we see a decrease in deep convection and Antarctic bottom water formation, as well as a decrease in AMOC and ACC. But also all these studies have shown that like the results vary with the amount and distribution of the freshwater. And in this talk, I'm going to try to show you in our work, we find that we also see a decrease in AABW, but also we find a transient increase of the AMOC and changes in the Southern Ocean upwelling. And this leads me to my research questions, which are how does the ocean circulation respond to meltwater from Antarctica, but also how does the horizontal and vertical distribution of meltwater matter for the response? And to study this, we use ORCA-1. So it's a global NEMO configuration with 1 degree horizontal resolution. And this configuration uses a climatological forcing representing the 1990s atmosphere, and also includes freshwater forcing from ice shelves at depth and icebergs. And so the simulation is already spun up before we start our perturbation experiments. And in the spin up, we see that the AMOC, ACC, and the Antarctic bottom water transport show transports comparable to observation. And also this simulation has realistic pathways of ventilation. This is what you can see on the maps here on the right. So in the center path here, you see the observation, or the bottom neutral density based on observation from the datasets of Koretsky et al. 2019. And we see that the bottom water here is formed on the shelves. And if we look at the simulation, we also see that highest densities are found on the shelf. And therefore we have realistic pathways. And to do our freshwater perturbation experiment, we include into this simulation anomalies for surface runoff. So all water which is melting on top of the ice shelf is entering the ocean at the surface level at the closest grid point. So in the model, it will cover all these grid cells in colored here on the map on the right. Then we also have the ice shelves, which adding freshwater anomalies at the depth of the ocean over the opening of the cavity, and also in the grid cells close to the coast. And lastly, we're adding icebergs, or we're adding anomalies for icebergs, which are spatially distributed over a monthly pattern of climatological melt, which is horizontally spread away from the ice shelf. So in a map, it can look like the map shown here on the right. If you're curious about the data set here, please have a look at webinar 2 or work package 2 webinar, where Anna is talking about the data set. And using these 3 anomalies, we run 4 experiments. So one is a control simulation without any anomaly. Then we're running an idealized simulation where we have a temporal and spatial uniform surface runoff anomaly of 0.1 Sverdrup. For those who are familiar with the modeling community may know that this is part of the SOFIA Tier 1 Entwater experiment for ocean, and we do it here in an ocean-only configuration. Then we run a realistic simulation where we have a spatial temporal variable anomaly for surface runoff, icebergs, and ice shelves. So we add anomalies in all horizontal, vertically, in all 3D variations. And the last one we run is a SEMI, we call it, which is a spatial uniform surface runoff anomaly with temporal variability, meaning that we take all anomalies from the realistic and put them at the surface similar to idealized. And all those 4 experiments have in same that they have the same climatological forcing and roughly represent changes for 1919 to 2100. So if you're curious about the realistic data set we use in realistic and SEMI, we use the data set from Violin-Collin, which was presented in webinar of work package 3. And this data set provides a reconstruction from 1990 to 2020 for the 3 anomalies we implement in our model. And then we also use the projection provided by this data set for the high emission scenario. And this data set comes with the spatial variability as well for the different drainage basins around the Antarctic coast, as you can see here in the maps with the different colors. If we compare now just how much freshwater we add over time to our ocean, we see here in the purple line the time integrated freshwater in the idealized simulation, and in the solid black line the total in the SEMI and realistic run. We see that in 2100 we have roughly 3 times more in the idealized than in the SEMI and realistic, and the dashed line at the bottoms are the 3 components of the anomalies. So for the results, I would quickly walk you through our Antarctic bottom water transport, the AMOC transport, as well as changes in the Southern Ocean upwelling. Starting off with the Antarctic bottom water transport, we see here in the plot the time series from 1990 to 2100 with the different colors. So the black line is our control simulation, in blue is the realistic simulation, in green the SEMI, and in red the idealized. And we see that in the idealized, we have an instant response in bottom water and a decrease, while we have a time delay in SEMI and realistic. But then in SEMI has sort of the same pattern as the idealized, while the realistic simulation takes to up to 2050s until it decreases down. In the long term, all these 3 experiments have sort of the same transport. Then we also looked at the AMOC transport at 26 north, same colors as before. And you probably noticed that in the beginning, the idealized increases AMOC strength, and also the realistic and SEMI do the same. The idealized simulation also decreases over the time after roughly 50 years, while the other 2 remain quite strong throughout our simulated period. And we were curious of if the signal is particular to 26 north or different locations. So 26 north is here in the center of the Atlantic Ocean. And we investigated sections further south at 30, 34 south, and 47 north, which you will see here now. So the top one is the northern section, the middle one is the one we've seen before, and the bottom one is the southern one. And if you look at the timing of the increase, you notice that it's showing up first at 34 south, and then appearing at the other sections traveling northward. The same is for the green arrow and the green-blue lines. So this indicates that we have a signal coming from the Southern Ocean changing our AMOC transport as a transient response. And to do this, we looked at the density stream function in the depth latitude space. So here is an example how to read this stream function. So we have the depth, we have the latitude space. We have here in blue our lower cell circulation, where the water comes up to the surface and then forms bottom water and goes down. And the upper cell circulation, where the water also goes up and then travels as surface and intermediate water northwards. And this, what we see here, is from our control simulation with climatological forcing, nothing changed. And we also see that this doesn't change from 2009 to 2099. But if we now look at our idealized simulation, we see that our Southern Ocean properties changed a lot. And we see that the upwelling here in the upper part, around 50 degrees south, strongly increased in 2009, but also this increase is continuous throughout the simulation. So this increase of Southern Ocean upwelling explains the AMOC strengthening in the beginning. And we identified that this is a result of a reduced compensation between Ekman and eddy-driven overturning due to the changes in the stratification from the freshwater. And to finally summarize everything, so we've seen that we have a decrease in Antarctic bottom water in all simulations, but we noticed that the freshwater distribution is important in the first 50 years, while in the long term, the responses are very similar. And we also saw that we have a rapid slowdown in the 2050s and realistic. Before that, it was semi-stable. Further, we have seen that we see an increase in Southern Ocean upwelling, which leads to an increase of AMOC in a transient response. And also, since the patterns between semi and realistic were very similar, but different to the idealized, that the AMOC response is more dependent on the amount of freshwater released. And yeah, that's the work. And thank you for listening.
Thank you very much, Birte. Our last speaker for today's seminar is David. David Chandler is a researcher at NORCE with expertise in ice sheets and climate modelling. His work explores how freshwater forcing from ice sheets reshapes ocean circulation and stratification, and how these shifts propagate across basins to influence global climate patterns. David will talk about global impacts of freshwater forcing. So thank you, David. I'll hand over to you.
Hi, thanks for that. Let's just get this sharing again. Can you see that? Is it in?
It's not in presenter mode yet.
Let's try that.
Yep, now it's good.
Okay, that's all good. Great. So yeah, in this talk, it's really very much continuing the theme of Birte's talk. And we've in some senses done quite similar experiments. But in this case, using an Earth system model rather than just an ocean model. So we also capture the feedbacks between different parts of the Earth system that you're not getting in just an ocean model. So yeah, so if we're wanting to look at sort of global scale feedbacks between the Antarctic and its freshwater fluxes and the rest of the climate system, we can show first a few examples where we find that the impacts of Antarctic freshwater fluxes are very much not confined just to the Southern Ocean. And I guess Birte has already shown that a little bit with the AMOC in the North Atlantic. So how far does the influence of Antarctic freshwater fluxes extend? Which other parts of the Earth system are influenced, and how are those influences? What are the underlying processes, feedbacks? And yeah, an Earth system model is a great way of trying to answer these questions. Of course, at the expense of a lot of computation time. And in our case, we're using the Norwegian Earth system model, which is one of the models that contributed to CMIP 6 and will hopefully contribute to CMIP 7 in next year. So this contains individual models for all the different components of the Earth system, and they're all linked together by the coupler, so they can all talk to each other. So it includes the atmosphere, ocean, sea ice. It includes the Greenland ice sheet, but not the Antarctic ice sheet. So the Antarctic ice sheet freshwater fluxes are added as an extra forcing. And then it's also containing like a land component and rivers as runoff. So I first wanted to show that these types of experiments, which are called hosing experiments, where we just add water to the Southern Ocean, they're not really new. 20 years ago, I think the first one was done by Glenn Richardson. And in his case, they were using, I think it was one of the UK models. And they just added a pulse of fresh water around Antarctica, ran the model for 10 years, which isn't actually very long in comparison to recent experiments. But they already got a lot of cooling in the Southern Ocean, which I think has probably been found in every hosing experiment since then, as far as I know. But after, well, within the 6 to 10 years, they also found some significant changes in the air temperature in the Northern Hemisphere as well, at least regionally, not everywhere. So they already showed that the Antarctic freshwater fluxes have a global response, at least in their model, in that setup. And then, yeah, a bit more recently, just thought I'd pick this one out. This was an Australian model, which is why Australia is plotted in the centre rather than the edge. They have been looking at a warming scenario. So this is SSP585, and then adding extra fresh water into that to simulate the effects of warming on the Antarctic ice sheet. And in their case, I think in the last 20 years of that 100-year simulation, they found quite a lot of less precipitation over the Southern Ocean. But also there are some parts of the Northern Hemisphere where there's some significant precipitation changes. So I think depending on the models, depending on the experiments, find that the Southern Ocean, Southern Hemisphere response is quite consistent. And then if I picked out lots of different examples of this, you'd probably find that the Northern Hemisphere response, there's often something significant that occurs, but it's not always the same. So one of the things we're going to look at some point is trying to look at a whole ensemble of models, probably in the Xabier experiment that Birte was talking about, to see if we can get a more consistent story for the Northern Hemisphere. Anyway, in our case, going back to NORCE, we're doing 2 main experiments. One is a conceptualized experiment where we're just adding constant amount of fresh water around Antarctica. And this is following the Xabier protocol that Petra was just talking about. So it's 0.1 sieverts, which is 3,000 gigatons a year. It sounds a lot. It's about 1.5 times the amount of fresh water that's coming off Antarctica at the moment, roughly. And that's in addition to what already is coming out. So it's a big signal. And that's just added everywhere around the coast of Antarctica. And then in the second experiment we're doing, this is kind of a more realistic projection to 2300. Again, using the same Antarctic freshwater fluxes that Coulon has published and that Birte is using with NEMO. And we haven't finished this one yet. It's only at, well, so far 2170. Yeah, I think that the main difference between this setup and Birte's is that in our case, we're also including the climate warming. So Birte was using constant climate, give or take, I think it's 1990s climate, and we're using it, the full warming scenario. So the climate is warming and the freshwater fluxes are increasing. I haven't got time to really go into a lot of different results, but I'm just going to show a few examples. First, looking at sea surface temperature, and I've split the response into zonal means for different parts of the world. And if we start in the middle plot, the black line shows this clear cooling of sea surface temperature. These are anomalies in the freshwater perturbation experiment compared to the control. So there's clear cooling, and that's the common Southern Ocean cooling we get in all these different hosing experiments. on that same plot, you also see in orange is the northern hemisphere mid-latitudes, and there's no cooling to start with, but after about 50 years or so, there's very strong cooling, and then for the rest of the experiment, on average, there's a sort of cooling signal of about 1/4 degree or so. And then also in the tropics, there's a little bit of cooling, also by about 1/4 degree. And even in the Arctic, which is the pale purple plot on the line on the left-hand plot, there's a little bit of cooling after, again, about 50 years. So this at least this sea surface temperature signal is extending all the way to the Arctic. And if you look at some maps, actually, compare the SST response with the changes in sea ice concentration, we find in both hemispheres the changes in, well, the increases in sea ice concentration are very closely linked to surface cooling. It's not perhaps very surprising. And again, even in the northern hemisphere, in the Arctic, we're finding increasing sea ice in areas where there's cooling. Not quite sure what's the underlying process here. How's that response getting there? Is it salinity driven? Is it through the atmosphere? We're not sure, so that's something we're going to have to look at in more detail. And then moving on to the more realistic scenario where we've got the increasing freshwater and the increasing and global warming. So this is with the SSP 585 scenario. I've plotted on this one first, just so you can see how much freshwater we're adding in this experiment, and it's the black stepped line is the freshwater anomaly we're applying in addition to whatever the model is simulating. And just for comparison, this 3,000 gigatons per year from Xabier is the red dotted line, not over these same years, but you can see that in this realistic scenario, there's actually very little freshwater added for the first sort of 60, 70 years, and it really, really quickly ramps up, goes past how much there is in Xabier, and then by 2200 it's really quite a lot. But because we've only run so far until 21, well, I'll show you results until 2150, so you can see that that's only really just starting to kick in, so the signal is not that strong yet. And I just thought I'd pick out the zonal mean sea surface temperatures again, because that's what we already looked at for the Xabier example. And here I've plotted the actual temperatures rather than the anomalies. And so far by 2150, you can see the dotted lines are the SSP 585 scenario without any extra freshwater, and then the solid line is the SSP 585 with the extra freshwater. And you can see so far they're really tracking each other very closely. So at this point, there's not a huge influence of the hosing, at least for SST. I think that the AMOC was also following the two experiments were very close sea ice. So everything we've looked at so far, these two experiments are doing basically the same thing. And one reason that might be the case is that I think with the Xabier type experiments where it's adding lots of fresh water to a pre-industrial climate or a sort of present day climate, this sort of Southern Ocean cooling response is driven by stratification. So the fresh water that you're adding greatly increases the stratification in the Southern Ocean, and that's what leads to the cooling and the increasing sea ice. But with the warming scenario, I think the global warming itself is it already causing increasing stratification, and also the warming is also in itself decreasing sea ice. So the chances for this sort of stratification related cooling and sea ice increase are that chance isn't really there in the SSP 585 scenario, which I think is why at the moment we're not seeing so much response. But it'll be interesting to see once we get into 2200s where there's really a lot of fresh water. Quite looking forward to that model continuing and we'll see what we get to there. So I think a quick summary, these conceptual experiments really show quite nicely that the Antarctic freshwater fluxes can have a global impact when you're looking at pre-industrial climate. The projection in our case doesn't show so much influence of the freshwater fluxes, but of course then there was the Australian model I showed you the example of earlier on, where there was some regional impacts of freshwater fluxes under SSP 585. So yeah, again, be interesting to look regionally at this, at our results. And we're going to look in more details at the Northern Hemisphere, mid-latitude and Arctic response, both in the sphere data and maybe within the SSP 585 scenario. Yeah, we need to finish our projection to 2300 and see if stronger response emerges later. And then once we have found some differences or responses, then yeah, getting into the mechanistic understanding, what's causing them, and what's transferring this southern hemisphere responses to the northern hemisphere. And I think there's going to be quite a lot to look at there. So I'll stop there and then yeah, see if there's any questions. Thanks very much.
Yeah, thank you very much, David. And so now we're going to enter the Q&A section of the webinar. And so just a reminder, if you do have any questions for any of the presenters, to please type them in the Q&A. And I see we already have a couple. We have one question to Birte. Do the depths at which meltwater is released from cavities change in time in realistic scenarios? And how important are icebergs in the SSP 585 scenario?
Yeah, thanks for the question. For the first one, if the depth changes, it's not, we're using like a fixed depth throughout the simulation. So it's every time the same depth. And for the second one, how important are the icebergs? I think it depends on what length you're looking at. For example, in my simulations where we go up to 2100, icebergs still contribute a lot of fresh water compared to, for example, the surface runoff. But in the long term, icebergs are expected to contribute less compared to the surface runoff or ice shelves. So yeah, for my work, the icebergs are still quite important. Yeah. Thank you.
And another question, someone says, hello, thank you for your presentations. I have a question about David and Birte's presentation. Do you think that a strong freshwater anomaly due to sea ice melt or Antarctic ice sheet melt can have an effect on the speed of the ACC? And how could this anomaly affect, in return, the global ocean circulation? I don't know whether David or Birte want to jump in on that.
Should I go? I can go first quickly if you want. Yes, so the added freshwater does decrease the speed of the ACC in our simulations, and I think in Birte's simulations, is that right? I think this is quite a common response across other models as well. Melting sea ice, I don't know how much that contributes to ACC slowdown. Not sure for the people who have looked at that. Birte might know about that one. And then in terms of global circulation, so Birte was talking about a bit about the AMOC and the response of the AMOC to the freshwater forcing. Actually, in our case, with the Xabier protocol, we actually don't find any change in the AMOC. We only find a change in the ACC, and you have a decrease in the ACC and a decrease in Antarctic bottom water formation, I think. But beyond that, we don't get much changes. But yeah, maybe Birte's got some more ideas on it.
Yeah, so I can add to David that in all three of my experiments, we see at the end of 2100 the same ACC transport. There are some differences in the patterns how the ACC decreases. But yeah, we haven't really looked into the ACC speed more in detail than just computing it. Yeah, I think that's all I can add.
I guess in terms of the the sea ice part of the question, the actual volume of fresh water from the sea ice melt is pretty small, isn't it, compared to the amount of adding from the Antarctic ice sheet? So maybe it would be quite minor. I'm guessing it's quite a small amount of water.
Yeah, thank you. And yeah, if you have any follow-up questions to the answers, yeah, please feel free to add. So this person already replied and said, okay, thank you for your answers. My name is Sophie. Yeah, Sophia Damaraki was that question was from. So thank you for the answer. And then we have some other questions. This one's for Petra. So working in a multicultural and multidisciplinary team has its challenges and rewards. How did Work Package 5 succeed in bringing experts together?
Yeah, so that's not really a scientific question, but more of how we work as a team. Thanks for asking that. I personally still think it's very interesting to work in European teams because you get indeed to learn a lot about different cultures, also from outside of Europe. And I think that's really rewarding. To work across all the different disciplines teaches us certain things. It teaches us also to be very specific. For example, some simple examples in our work is often colleagues talk about ice, but what do we actually mean? Do we mean the ice on land or do we mean the sea ice? And sometimes you get whole conflicts about that. So I think it's nice if we all to learn how to work across different disciplines and to make it very precise what you're actually saying. And then, of course, it's also fun. It is good to the challenge with working so across different countries and different cultures is that we unfortunately don't always have enough time to meet in person. And in person, you can clarify things much easier and quicker. So annual meetings and so are very, very important for these kind of large European projects. Of course, we meet a lot online in shorter meetings, but we cannot really do this without any personal interactions, I think. I hope that answers your question.
Yep, that's excellent. Thank you. And then a question for Zhetao. What is the biggest uncertainty we still face when trying to understand water mass changes?
Okay, thank you for your questions. So I think the biggest uncertainty there are and I think it's about the data quality before the Argo period. And you know that in the South Atlantic before the Argo period and the observation are mainly in some cruises and in some chances. And this are repeated maybe 1 year or 2 years or more than 10 years. So it means that when we detect the water mass before the 2005, the data uncertainty are really large. The in-sample gap is really large, and this is make it really challenge about the long-term change and the multi-decadal change, and we didn't have so much high confidence about whether what we observed it is the real signal. So this is more about the ocean observations network. So that is why we want to improve the ocean observation the network in the South Atlantic to gain more attentions and some fundings to improve the network. Yes.
Excellent, thank you. And a question for Rachael. How long would you expect it to take for a signal in the Weddell Sea to be seen in the South Sandwich Trench data?
Thanks. So the previous work has shown that it takes around a month for anomalies in the Weddell Sea to reach the Orkney Passage. So that's the difference between the M3 moorings and the OP moorings. So we'd expect at least as long as that, probably more. So we need to look at the bathymetry to work out exactly how long we'd expect that given the speeds that we know, the current speeds that we know. So probably at least double that, so at least over 2 months, but hopefully less than a year because that's how much data we have.
And a question for Xabier. How does water mass archaeology of a water mass change the way we think about future observations?
Yeah, thanks for the question. It's interesting, right? Because when you're taking observations, you are sampling the present, but these water masses, they came from far away, so you are also sampling the past. So there are water masses that you can target that will give you lots of information at different time scales. So I think it's something to take into account when we are planning also future campaigns and future observations, to think what are the time scales of that water mass that was at the surface, and think a bit more on a water mass space rather than on a geographical space, so we also avoid redundancy in the data.
Yeah, excellent. And a question for David. Bronzali et al. 2018 is find a substantial impact of meltwater on global mean SST in SSP 5 to 8.5 over the 21st century. Any ideas why the NORCE is less sensitive? Is it merely due to different freshwater forcing?
It could well be. I'm not sure how much freshwater bronze layer used, and it's worth bearing in mind, of course. Yeah, in our experiment, we've just done we've used Coulon's Coulon et al. Freshwater forcing, so it's pretty weak freshwater forcing as far as 2080 or 2090. So yeah, I think that'd be the main reason, is that just our freshwater forcing is very weak until nearly the end of this century, and then it only picks up near the end. Yeah.
Okay. Thank you. And I don't see any more questions there. So give everyone one last chance to get in a last minute question. But yeah, I would like to just finish by warmly welcoming all of today's speakers for sharing their research from their ocean ice work in Work Package 5. And thank you to everyone who participated today and took part. A recording of the webinar from today and all the previous webinars that were mentioned during the presentations will be available on EPB's YouTube channel in the coming days. So please keep an eye on that for a recording of this webinar. And feel free to reach out if you have any questions. So thank you, everyone. And I wish you all a good rest of the day and a happy week.
Thank you.